Hi everyone, I am Buvana Ganesh. I work under Professor Paolo Palmieri in University College Cork, and I thank FPS 2020 for giving me the opportunity to present my work on a survey of advanced encryption techniques used for database security in today's talk. Let's proceed. Needless to say, database security is very important in this age of big data. We face data breaches even in big corporations like McAfee, LinkedIn, and so on, which emphasizes the need to keep improving security. Database as a service is increasingly relevant because of the storage and computational capacity provided by clouds, but they are generally not trusted. Data from which a lot of insights can be derived are unutilized because of lack of access, either due to hierarchy or compliance issues. Encryptions can actually solve this problem. After gaining access, mining and warehousing become the obvious next steps. We also need secure search in order to achieve this. The methods used now to protect data are predominantly access control based. For data at rest, services like Azure, Oracle, AWS, etc. use transparent data encryption in different forms, and for data in transit, transport layer security is used. In this work, we would like to look at providing provable security techniques in order to protect data in use, which is when a user accesses and queries data to use it. Let us understand why we take certain ways in order to encrypt databases. Because encrypting just the data stands risk to access pattern disclosures and other obvious attacks. So we have to protect the database, the query engine, the underlying data structure, as well as the output. So in order to understand what we're actually trying to protect, let's look at this TPCH query. So in this query, if we break it down, there is a sum operation, there is a multiplication, there is comparison as well as search. So in order to perform this query on encrypted data, we would need encrypted sum, encrypted multiplication, encrypted comparison, and encrypted search. So in order to do this, we can use certain property preserving functions in a traditional database to achieve our result. The second one would be to change the underlying data structure of our database from normal B trees or B plus trees to a privacy preserving data structure, which we'll look at more about in the coming slides. Another method would be to use trusted execution environments like XGX in order to do these operations inside the SGX's limited storage. Another very common method would be to combine access control policies with encryption techniques in order to achieve the same result. Let's tackle one property at a time by looking at property preserving encryptions. The first would be searchable encryptions, of which the symmetric searchable encryptions are the most popular. In a standard scheme, the owner shares encrypted files along with a secure index to the server. The user queries for a keyword and it is retrieved if it exists through a trapdoor, which is pre-programmed in the secured index. There are public key models available for this also, though they are less popular. Security for these schemes are given by indistinguishability under chosen keyword attacks or chosen query attacks, which are similar to the proofs given for chosen plain text attacks. The next property would be comparison. So order preserving encryptions work only on numerical data and they preserve their order. They can be mutable, modular, multi-provider, etc. based on the scheme. Their security is proved through indistinguishability under ordered chosen plaintext attack where nothing except the order of the plaintext is revealed. The Boldireva scheme is the most popular even though it is extremely leaky because of its ease of implementation. The last property would be arithmetics. The homomorphic encryption category enables addition and multiplication on encrypted data. Popular corporations have released libraries like MS Seal, Microsoft Seal, and IBM HElib, which use popular schemes like BFV and CKKS in order to achieve these properties. These allow for computations to be performed on encrypted data instead of the usual way where the data has to be decrypted in the service provider for computation. Let's start by looking at the most implemented type in database encryption schemes, where the underlying database does not change, but instead layers of encryptions and or proxy server is introduced for encryption and key management. It can be multi-key, multi-cloud or multi-server. So basically a modular structure which uses property preserving encryptions and access policies in order to query the data. A popular model would be ARCS, DB mask, which uses access policies combined with attribute-based group key management, and CBED, which uses a special kind of encryption called additively symmetric homomorphic encryption. The scheme that kick-started this practice of practical encrypted databases is DB from Popa et al. In 2012, which has a passive model. It has a proxy with onion layering using onion keys. For example, if you look at the model below, the onion ordering model would imply that a query sent to the proxy server would process the join operation first, and then it would process the order operation through an order preserving encryption, and then it goes to the randomized layer which performs AES on the data to make up for the security that was weakened by the order preserving property. So if we look at the performance, understandably, CryptDB is slower than MySQL by about 26% and cannot combine queries well. It encrypts the entire database every time, and so this makes it slower. Though they show in CPA level security, inference attacks cause a lot of damage, and this can lead to a bad model. When we look at the pros and cons, this type of models are the easiest to implement with practical time and storage, but the compromise comes from the security aspect, as it can lead to database reconstruction. The second type of schemes are based on the underlying data structure and are generally more theoretical in nature. Their aim is to eliminate property revealing schemes, hide the access patterns, and construct data structures that support these properties like inverted indices, searchable encryption indices, or ORAM. The underlying B or B plus trees are replaced with Bloom filter trees or fast AVL trees, which are self-balancing in order to support inserts and updates dynamically. Some examples are blind seer with broom filter and garble circuits, CISO PIR and OS PIR, which are essentially searchable encryption schemes which support the full framework. As an example, let us look at Oblix, which is a recent work. It is secure against malicious attackers who can actively tamper, but the DB is unchanged. The model uses doubly oblivious ORAM, which is much like path ORAM shown below, which splits the entire database into blocks and stores them in a self-balancing binary tree as mentioned before, which reshuffles every time a query is performed. Instead of standard position maps, doubly oblivious multi-maps are used in Oblix. It consistently refreshes the tree and supports updates hence. Now, analyzing the pros and cons, this group of schemes score really high in security and functionality, but hit very hard in the performance aspect. For example, blind seer is 4 times slower than MySQL when you compare it to CryptDB's 26%. The next category of schemes involve hardware, specifically trusted execution environments like ARM Trust Zone or software guard extensions from Intel, which isolate a portion of your storage and make it secure with AES GCM for any data entering or leaving the trusted hardware. Calculations are up to 4 times slower than MySQL, which without any other extra components. Some popular examples are Trusted DB, the first of this kind in using an Intel secure coprocessor, Cipher-base, and ObliDB, which actually combines SGX along with ORAM in order to hide the access patterns. Let's look at a simple example from Microsoft Research, Enclave DB. They achieve security against a malicious model using just the software guard extension. Again, there are no changes to the database made. This particular model runs on a Hackathon engine, whereas there are other models which run on PostgreSQL, etc. So let's look at the pros and cons. It is very easy to integrate an SGX to your existing DBMS, and it is available for installation as it's open source if you have an Intel processor. The downside, of course, would be limited storage available in the SGX because you're isolating a portion of your hardware, and the need for your service provider to comply to using the trusted execution environment itself. Moreover, SGX isn't safe on its own and requires something like ORAM or other components in order to achieve proper security. Before we move on to analyze the types that we saw before, let us look at the current practices in industry. The schemes mentioned in this survey cannot be implemented on a large scale because the performance versus security trade-off is not anywhere near optimal. The best schemes from industry use transparent data encryption, but some companies like BitClass work with something similar to the encrypted traditional databases that we saw before. The ARCS model is utilized by MS Always Encrypted, available in Azure and Microsoft SQL. Google Encrypted BigQuery used similar models, but the project is not active now. The Gartner quadrant is always a good way to evaluate the best performance for the year, but we can clearly see that there has to be a transition made from theory to practice. Now let's analyze the performance aspect of the schemes. For each scheme, we have to look at whether we should encrypt the data beforehand or only during the computation and its respective complexity. Also, storing the encrypted data directly implies that the size will increase, so does the storage. So these two factors are give the highest impact, and so we provide comparisons based on performance and security and find that no one scheme excels in all aspects. So we break it down to components used, benchmarks, etc. for performance, and similarly for security we look at the primitives used in the schemes and the security achieved. For a number of schemes we have provided a short description of the working literature and security in order to understand how it works. Here's a small example of comparisons between the PPE schemes along with ORAM. Complexity is measured differently for all types of schemes, and not enough information is available to reconstruct or construct the encryption at times. So the numbers you see are based on those of the best schemes available in those categories. Looking at the security aspect, we see two kinds of security proofs being used. Game-based proofs can read semantic security or indistinguishability under chosen plain text attack level security in the maximum because ciphertexts are designed to leak properties in encrypted traditional databases and therefore cannot achieve CCA level security. The real ideal simulation paradigm is given for proofs involving ORAM or searchable encryptions. Variations of both game-based and simulation-based proofs are available for weaker versions of security to establish proof for composed models. Threats can be malicious or passive, and Prior knowledge for attacks are assumed beforehand for full query or document or partial or query or document recovery. Now let us discuss why traditional encrypted databases may not be the most secure. Cache and team present that property preserving searchable encryptions leak info at 4 different levels, where substitutions leak the most amount of information and ORAM or homomorphic encryption reveal the least. But encryption cannot be avoided under any circumstance. Almost all schemes we have discussed enter one of these categories and are therefore prone to the attacks that we shall be discussing soon. In the figure, we see that L4 leakage is deterministic from substitution and so can be easily decrypted with some prior knowledge. For L3 level attacks, it is obvious as the data is numerical at some stage. The L2 leakage, for L2 leakage, the presence of a deterministic cipher again leaks data that can be decrypted by correspondence. But in L1, we see that the shuffling and the non-determinism makes it harder to decrypt, but it is still possible. The leakages are bound to bite back, right? So let's look at the attacks arising from the leakages. Database reconstruction proposed by Grubbs uses statistical learning theory in order to reconstruct the databases along with the volume of the database. This is approximately done by about an epsilon error. Injection of records from malicious users creates partial query knowledge, and this is very valuable for launching attacks. Inference attacks uses the data that is revealed offline by OPE-like encryptions, effective especially on CryptDB. When we don't use ORAM or some other oblivious data structure, inference attack can leak access patterns. Count attack, the only one that can impact even L1 leakages, simply counts matching records from recovered queries and uses prior knowledge. If we look at the table, we can easily see that most schemes we've discussed so far have fallen under at least one of the categories, and also encrypted traditional databases are prone to more attacks than the other category. Schemes based on privacy-preserving data structures clearly hold more security as they all fall under L1 leakage. For hardware-based attacks, side channels are the most common out of all for the trusted execution environments. Memory mapping and cache timing attacks make use of logs and record which part of the memory is frequently used and how frequently to launch denial of service or other attacks. This can be prevented by using ORAM, but that again will cause L1 leakage. If you have a database scheme, what would be the things that you would look at in order to see if it is a secure scheme or not? So you would be looking at the complexity in terms of time and storage and compare it to a standard database management system like MySQL. Then you would be looking at the individual components and their threat levels. So it is ideal to go for schemes involving privacy preserving data structures and to look at encrypting data versus the computation and what sort of untrusted entity you are dealing with, whether it's an untrusted user or an untrusted server service provider. The security of the Compose framework is as important as that of the individual components, because even though the individual components are secure, the whole framework may not be so. The ease of usage is very important because there may be one master key and 3 other keys, and every employee cannot be expected to remember so many passwords. Changes to databases should not affect the interface with which many people operate database management systems, because ease of usage is very, very important. There should be no compromise on confidentiality, integrity, or availability, the trio, because if even one of those get compromised, then we are not providing ideal security. The security versus performance trade-off is very, very important, because we see before that even though the privacy preserving data structure models give the highest amount of security, we are not able to practically implement them. Trying to find trade-offs in order to make them more feasible is very important. The last one would be to build your own scheme in order to check where exactly we would get flaws in terms of both performance and security. Finally, the outcome of the survey is to provide an introduction and overview into all the available methods for advanced database security in the hardware and software aspect. Being a recent field, the literature in the area is very dispersed, with a lot of different methods that are very hard to categorize, even with security proofs and benchmarks which are highly varied. Uh, I hope that the survey will also point out which techniques are secure and easy to implement. Open problems like secure matrix multiplication, secure dynamic operations, and even in the future data mining, which will be possible because of privacy preserving machine learning, can also be attained through database security. Thank you all for your attention. I thank the SFI for sponsoring my talk, my education. Thank you. Now would be the time to put forth your questions.